Aliens. Whenever people mention the word aliens, I'm sure most of us think of humanoid beings crashing to Earth in their flying saucers, brandishing guns. But that isn't what the scientists are necessarily looking for. They're searching for planets that may contain the right ingredients to sustain some form of living creature. They are also looking for microorganisms that may evolve into some form of a living, breathing, sapient being in hundreds of millions of years, just as we did on Earth. As technology improves, scientists can send their rockets further and further into outer space. They haven't yet found any human-like creatures, but they have made some very significant discoveries. Come with me now as we fly into outer space and take a deep dive into the real world of aliens. Extraterrestrial life is a theoretical life that may occur on another planet. Such life might range from simple single-celled organisms to intelligent and even sapient beings, possibly far more advanced than humanity. The science of extraterrestrial life in all its forms is known as astrobiology. Since the middle of the 20th century, active ongoing research has been conducted to look for signs of extraterrestrial life. Depending on the search category, methods range from telescope and specimen data analysis to radios to detect and send communication signals. The concept of extraterrestrial life, particularly extraterrestrial intelligence, has had a significant cultural impact, chiefly in works of science fiction. Over the years, science fiction has imagined a wide range of possibilities and influenced public interest in extraterrestrial life. There is an ongoing debate over the wisdom of communicating with extraterrestrial intelligence. Some encourage aggressive methods to make contact with intelligent extraterrestrial life. Others argue that it may be dangerous to call attention to Earth, citing the tendency of technologically advanced human societies to enslave or wipe out less developed societies. Alien life, such as microorganisms, has been presumed to exist in the solar system and throughout the universe. This hypothesis relies on the vast size and consistent physical laws of the observable universe. According to this argument, made by scientists such as Carl Sagan and Stephen Hawking, and notable personalities such as Winston Churchill, it would be doubtful for life not to exist somewhere other than Earth. This argument is embodied in the Copernican principle, which states that Earth does not occupy a unique position in the universe, and the mediocrity principle, which states that there is nothing special about life on Earth. The chemistry of life may have begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. Life may have emerged independently at many places throughout the universe. Alternatively, life may have formed less frequently, then spread by meteoroids, for example, between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these studies, this process may occur outside Earth on several planets and moons of the solar system and planets of other stars. A study published in 2017 suggests that due to how complexity evolved in all species on Earth, the level of predictability for alien evolution elsewhere would make them look similar to life on our planet. One of the study authors, Sam Levin, notes, like humans, we predict that they are made up of a hierarchy of entities which all cooperate to produce an alien. At each level of the organism, there will be mechanisms in place to eliminate conflict, maintain cooperation, and keep the organism functioning. We can even offer some examples of what these mechanisms will be. There is also research in assessing the capacity of life for developing intelligence. It has been suggested that this capacity arises with the number of potential niches a planet contains. The complexity of life itself is reflected in the information density of planetary environments, which can be computed from its niches. Life on Earth requires water as a solvent in which biochemical reactions occur. Sufficient quantities of carbon and other elements, along with water, might enable the formation of living organisms on terrestrial planets with a chemical makeup and temperature range similar to that of Earth. Life based on ammonia rather than water has been suggested as an alternative, although this solvent appears less suitable than water. It is also conceivable that there are forms of life whose solvent is a liquid hydrocarbon, such as methane, ethane, or propane. About 29 chemical elements play active roles in living organisms on Earth. About 95% of living matter is built upon only 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements form the basic building blocks of virtually all life on Earth, whereas most of the remaining elements are found only in trace amounts. The unique characteristics of carbon make it unlikely that it could be replaced, even on another planet, to generate the biochemistry necessary for life. The carbon atom has the unique ability to make 4 strong chemical bonds with other atoms, including other carbon atoms. These covalent bonds have a direction in space, so that carbon atoms can form the skeletons of complex 3-dimensional structures with definite architectures, such as nucleic acids and proteins. Carbon forms more compounds than all other elements combined. The great versatility of the carbon atom and its abundance in the visible universe make it the element most likely to provide the basis for the chemical composition of life on other planets. Macroevolution. Some bodies in the solar system have the potential for an environment where extraterrestrial life can exist, particularly those with possible subsurface oceans. Should life be discovered elsewhere in the solar system, astrobiologists suggest that it will more likely be in the form of extremophile microorganisms. According to NASA's 2015 astrobiology strategy, life on other worlds is most likely to include microbes, and any complex living system elsewhere is likely to have arisen from and be founded upon microbial life. Important insights on the limits of microbial life can be gleaned from studies of microbes on modern Earth, as well as their ubiquity and ancestral characteristics. Researchers found a stunning array of subterranean organisms, primarily microbial, deep underground, and estimate that approximately 70% of the total number of Earth's bacteria and archaea organisms live within the Earth's crust. Rick Colwell, a member of the Deep Carbon Observatory team from Oregon State University, told the BBC, "I think it's probably reasonable to assume that the subsurface of other planets and their moons are habitable, especially since we've seen here on Earth that organisms can function far away from sunlight, using the energy provided directly from the rocks deep underground." Mars may have niche subsurface environments where microbial life might exist. A subsurface marine environment on Jupiter's moon Europa might be the most likely habitat in the solar system outside Earth for extremophile microorganisms. The panspermia hypothesis proposes that life elsewhere in the solar system may have a common origin. If extraterrestrial life was found on another body in the solar system, it could have originated from Earth, just as life on Earth could have been seeded from elsewhere. This is known as exogenesis. The first known mention of the term panspermia was in the writings of the 5th century BC Greek philosopher Anaxagoras. In the 19th century, several scientists again revived the term in modern form, including Jöns Jacob Berzelius in 1834, Kelvin in 1871, Hermann von Helmholtz in 1879, and somewhat later by Svante Arrhenius in 1903. Sir Fred Hoyle and Chandra Wickramasinghe are influential proponents of this hypothesis, who further contended that life forms continue to enter Earth's atmosphere and may be responsible for epidemic outbreaks, new diseases, and the genetic novelty necessary for macroevolution. Directed panspermia concerns the deliberate transport of microorganisms in space, sent to Earth to start a life here, or sent from Earth to seed a new stellar system with life. The Nobel Prize winner Francis Crick and Leslie Orgel proposed that an advanced extraterrestrial civilization may have purposely spread seeds of life, but considering an early RNA world, Crick noted later that life may have originated on Earth. The spacecraft Messenger found evidence of water ice on Mercury. Based on studies reported in March 2020, parts of the planet Mercury may at one time have been habitable. The study suggests that it is possible that life forms, albeit primitive microorganisms, may have existed on Mercury. In the early 20th century, Venus was considered to be similar to Earth for habitability, but observations since the beginning of the space age revealed that the Venusian surface temperature is around 467 degrees centigrade, making it inhospitable for Earth-like life. Between the altitudes of 50 and 65 kilometers, the pressure and temperature are Earth-like. Likewise, the atmosphere of Venus is almost wholly carbon dioxide, which can be toxic to Earth-like life. In September 2020, a paper was published announcing the detection of phosphine in Venus's atmosphere in concentrations that could not be explained by known abiotic processes in the Venusian environment, such as lightning strikes or volcanic activity. Furthermore, Venus likely had liquid water on its surface for at least a few million years after its formation. Humans have been speculating about life on the Moon since antiquity. One of the early scientific inquiries into the topic appeared in an 1878 Scientific American article entitled, "Is the Moon Inhabited?" Decades later, a 1939 essay by Winston Churchill concluded that the Moon is unlikely to harbor life due to the lack of an atmosphere. 3.5 to 4 billion years ago, the Moon could have had a magnetic field, an atmosphere, and liquid water sufficient to sustain life on its surface. Warm and pressurized regions in the Moon's interior might still contain liquid water. Several species of terrestrial life were briefly brought to the Moon, including humans, cotton plants, and tardigrades. As of 2021, no native lunar life has been found, including any signs of life in the samples of moon rocks and soil. Life on Mars has long been speculated. Liquid water is widely thought to have existed on Mars in the past, and now can occasionally be found as low-volume liquid brines in shallow Martian soil. The origin of the potential biosignatures of methane observed in the atmosphere of Mars is unexplained, although hypotheses not involving life have also been proposed. There is evidence that Mars had a warmer and wetter past. Dried-up riverbeds, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found. Nevertheless, present conditions on the subsurface of Mars may support life. Evidence obtained by the Curiosity rover studying Aeolis Palus Gale crater in 2013 strongly suggests an ancient freshwater lake that could have been a congenial environment for microbial life. Current studies on Mars by the Curiosity and Opportunity rovers are searching for evidence of ancient life as well as ancient water, including plains related to ancient rivers or lakes that may have been habitable. The search on Mars for evidence of habitability, fossils, and organic carbon is now a primary NASA objective. The only dwarf planet in the asteroid belt, Ceres, has a thin water vapor atmosphere. The vapor could have been produced by ice volcanoes or by ice near the surface, transforming from solid to gas. Nevertheless, water on Ceres has led to speculation that life may be possible there. It is one of the few places in the solar system where scientists would like to search for possible signs of life. Although the dwarf planet might not have living things today, there could be signs it harbored life in the past. In the 1960s and 70s, Carl Sagan and others calculated the possibility of microorganisms living in the atmosphere of Jupiter. However, the intense radiation and other conditions do not appear to permit encapsulation and molecular biochemistry, so life there is thought unlikely. In contrast, some of Jupiter's moons may have habitats capable of sustaining life. Scientists have indications that heated subsurface oceans of liquid water may exist deep under the crusts of the three outer Galilean moons, Europa, Ganymede, and Callisto. The EJSM Laplace mission was planned to determine the habitability of these environments. However, the program was discontinued due to a lack of funding. Like ESA's JUICE and NASA's Europa Clipper, similar missions are currently in development and are scheduled for launch in 2022 and 2024 respectively. Jupiter's moon Europa has been the subject of speculation about the existence of life due to the strong possibility of a liquid water ocean beneath its ice surface. Hydrothermal vents on the bottom of the ocean, if they exist, may warm the water and could be capable of supplying nutrients and energy to microorganisms. It is also possible that Europa could support aerobic macrofauna using oxygen created by cosmic rays impacting its surface ice. The case for life on Europa was significantly enhanced in 2011 when it was discovered that vast lakes exist within Europa's thick icy shell. Scientists found that ice shelves surrounding the lakes appear to be collapsing into them, thereby providing a mechanism through which life-forming chemicals created in sunlit areas on Europa's surface could be transferred to its interior. On the 11th of December 2013, NASA reported the detection of clay-like minerals, specifically phyllosilicates, often associated with organic materials, on the icy crust of Europa. According to scientists, the presence of these minerals may have been the result of a collision with an asteroid or comet. Europa's subsurface ocean is considered the best target for discovering life. The Europa Clipper, which would assess the habitability of Europa, is planned for launch in 2024. Like Jupiter, Saturn is not likely to host life. However, Titan and Enceladus have been speculated to have possible habitats supportive of life. Enceladus, a moon of Saturn, has some of the conditions for life, including geothermal activity and water vapor, as well as possible under-ice oceans heated by tidal effects. The Cassini-Huygens probe detected carbon, hydrogen, nitrogen, and oxygen, all vital elements for supporting life, during its 2005 flyby through one of Enceladus's geysers, spewing ice and gas. The temperature and density of the plumes indicate a warmer, watery source beneath the surface. Titan, the largest moon of Saturn, is the only known moon in the solar system with a significant atmosphere. Data from the Cassini-Huygens mission refuted the hypothesis of a global hydrocarbon ocean. They later demonstrated the existence of liquid hydrocarbon lakes in the polar regions, the first stable bodies of surface liquid discovered outside Earth. Analysis of data from the mission has uncovered aspects of atmospheric chemistry near the surface that are consistent with, but do not prove, the hypothesis that organisms there, if present, could be consuming hydrogen, acetylene, and ethane and producing methane. NASA's Dragonfly mission is scheduled to take off in 2026 and to land on Titan in the mid-2030s with a VTOL-capable rotorcraft. Small solar system bodies have also been speculated to host habitats for extremophiles. Fred Hoyle and Chandra Wickremesinghe have proposed that microbial life might exist on comets and asteroids. Rhea, Titania, Oberon, Triton, Pluto, Eris, Sedna, and Orcus may have oceans underneath solid frozen crusts, approximately 100 kilometers thick. Studies indicate that the liquid layers are in direct contact with the rocky core, which allows the efficient mixing of minerals and salts into the water. This contrasts with the oceans that may be inside larger icy satellites, like Ganymede, Callisto, or Titan, where layers of high-pressure phases of ice are thought to underlie the liquid water layer. Hydrogen sulfide has been proposed as a hypothetical solvent for life, and is quite plentiful on Jupiter's moon Io, and may be in liquid form a short distance below the surface. The scientific search for extraterrestrial life is constantly being carried out and updated. By September 2017, scientists had identified 3,667 exoplanets in 2,747 systems. They also found other planets and moons in our solar system that hold the potential for hosting primitive life, such as microorganisms. By the 8th of February 2021, an updated status of studies was reported, which considered the possible detection of life forms on Venus and Mars. Scientists search for biosignatures within the solar system by studying planetary surfaces and examining meteorites. Some claim to have identified evidence that microbial life has existed on Mars. An experiment on the 2 Viking Mars landers reported gas emissions from heated Martian soil samples that some scientists argue are consistent with the presence of living microorganisms. Lack of corroborating evidence from other experiments on the same samples suggests that a non-biological reaction is a more likely hypothesis. In 1996, a controversial report stated that structures resembling nanobacteria were discovered in a meteorite formed of rock ejected from Mars. In February 2005, NASA scientists reported that they might have found some evidence of extraterrestrial life on Mars. The 2 scientists, Carol Stoker and Larry Lemke of NASA's Ames Research Center, based their claim on methane signatures found in Mars's atmosphere, resembling the methane production of some forms of primitive life on Earth, as well as on their own study of primitive life near the Rio Tinto River in Spain. NASA's officials soon distanced NASA from the scientists' claims, and Stoker herself backed off from her initial assertions. Though such methane findings are still debated, support among some scientists for the existence of life on Mars exists. In November 2011, NASA launched the Mars Science Laboratory that landed the Curiosity rover on Mars. It is designed to assess the past and present habitability on Mars using a variety of scientific instruments. The rover landed on Mars at Gale Crater in August 2012. The Gaia hypothesis stipulates that any planet with a robust life population will have an atmosphere in chemical disequilibrium, which is relatively easy to determine from a distance by spectroscopy. However, significant advances in finding and resolving light from smaller rocky worlds near their stars are necessary before such spectroscopic methods can analyze extrasolar planets. To that effect, the Carl Sagan Institute was founded in 2014 and is dedicated to the atmospheric characterization of exoplanets in circumstellar habitable zones. Planetary spectroscopic data will be obtained from telescopes like WFIRST and ELT. The Green Bank Telescope is one of the radio telescopes used by the Breakthrough Listen project to search for alien communications. In August 2011, findings by NASA, based on studies of meteorites found on Earth, suggest DNA and RNA components, the building blocks for life as we know it, may be formed extraterrestrially in outer space. In October 2011, scientists reported that cosmic dust contains complex organic matter that could be created naturally and rapidly by stars. One of the scientists suggested that these compounds may have been related to the development of life on Earth, and said if this is the case, life on Earth may have had an easier time getting started, as these organics can serve as basic ingredients for life. In August 2012, and a world first, astronomers at Copenhagen University reported the detection of a specific sugar molecule, glycolaldehyde, in a distant star system 400 light-years from Earth. Glycolaldehyde is needed to form ribonucleic acid, or RNA, which is similar in function to DNA. This finding suggests that complex